so in this video lesson, I'm going to ask you to be reflective in what I'm doing. So I wrote, what am I doing here? So if we were to slide this down, having worked with nderiv before, I have some original function, and I've got my next function y2, and then I've got this function y3. What is it that I'm doing here? Or in other words, what is y3? y3 is the derivative of y prime, or of, f prime of x, or dy dx. Y3 is the derivative of the derivative of f of x. So it's the derivative of the derivative. And we're going to be talking about how we write that. But this is what we're looking at today, the derivative of the derivative, and what it means. So I say here, reflect for 2 minutes, for however long it takes you to make a connection. So I want you to pause the video when I open up this shade here, and I want you to try to figure out the connection between all three of the graphs. So we're looking at the function, its derivative, and the derivative of the derivative. So we've got f of x here, f prime of x here, and the derivative of f prime of x, which we're going to show the notation in a second, but it's f double prime of x, so the derivative of the derivative. So what can you learn from this? In other words, some questions that you might be wanting to think about. What happens what's true when f double prime of x equals 0? What's true when f double prime of x is greater than 0? What's true when f of x is concave up? What's the connection between all these? So this is what we're going to be getting into today. But before we jump into that, a notation that I already gave you, the second derivative of f, we write as f double prime of a, or y double prime, or another notation is, the derivative of the derivative, we write as d squared y over dx squared. So these are all ways that we can express the second derivative. And just to keep it general, so we're not talking about the derivative at some point a, double prime, f double prime of x. So it's the second derivative at x. Going back, what is this here? What is this notation? The limit as h approaches 0 of f prime of a plus h minus f prime of a over h. Well, this looks very familiar to this formula, which we've now looked at a bunch. This is the derivative of f. But now what we have instead, we've got this f prime. So this equation is the derivative of the derivative. It's f double prime of x, or y double prime, or d squared y dx squared. Okay, so this is all kind of conceptual, leading towards how does the second derivative affect the graph. So let's start off with when f double prime of x is greater than 0. So that's happening what's going on with the first derivative? Well, here's the first derivative. Here's y prime, y double prime, and y. And here's the second derivative. Or sorry, here's the function. So what we're doing is we're looking at when the first derivative is greater than 0, so we draw that in red. And when that's happening, we're looking, in this particular case, when x is greater than 0. So we looked up at the first derivative and noticed, well, the first derivative was looking like that, and the actual function is looking like it does in the blue. So let's try to maybe generalize that a little bit. What's going on with f prime of x? Well, when the second derivative of x is greater than 0, that means f prime of x is increasing. And when f double prime of x is greater than 0, what's going on with f? Well, f is concave up. So now, for whenever the second derivative is greater than 0, that means that the first derivative is increasing and the function itself is concave up. What about when f double prime of x equals 0? So that is right here, here, and here. What's going on with f prime of x? Well, with f prime of x, in this particular problem, we have a local min, but we could also have a local max. Some of you hopefully are drawing the parallels, looking at the connection between f prime of x and f double prime of x to f prime of x is analogous to looking at f prime to f. We're comparing derivatives. All right, when f double prime of x equals 0, what's going on with the function itself? Well, what's going on right there? What does that look like? Something we've been talking about. There we have a point of inflection. So anytime where the second derivative equals 0, the function itself is going to have a point of inflection. So, putting this together, whenever the second derivative is greater than 0 on some interval, if the second derivative is greater than 0, then f prime of x must be increasing. And if the second derivative is less than 0, then the first derivative must be decreasing. Well, how does that reflect f of x? So we said here f double prime of x is greater than 0. And when it's greater than 0, my slope is increasing. So we see the slope's increasing. And therefore, we get something that's concave up. And when f double prime of x is less than 0, we know that f prime of x is decreasing. And all of these slopes here are decreasing, which corresponds to something being concave down. So we now know that when f prime of x is greater than f double prime of x is greater than 0, our function is concave up. And our derivative, first derivative, is increasing. And when f double prime of x is less than 0, our function is concave down, and our first derivative is decreasing. So try this on your own. Pause this, and what I want you to do is find the inflection points of this function. So pause this, and then see if you can get an answer. Try whatever strategy you have, and then unpause the video and watch the method in which I'm going to use to solve this. So we know that there's going to be a point of inflection, POI, point of inflection where y double prime equals 0. And more than just where y double prime equals 0, where y double prime goes from either a positive to 0 to negative, or negative to 0 to positive, where it must change concavity. Because where y is positive, that means it's concave up, and where it's negative, that means it's concave down. And that's from last slide here. Whenever it's positive, it's concave up. When it's negative, concave down. So if it goes positive, 0, negative, that means it goes concave up to concave down. And there would be my point of inflection. And if we have negative, 0, positive, that means concave down to concave up, looking like this. Or that would be my point of inflection. So to answer this question, what I need to find is where does the second derivative equal 0, and then just to make sure that around that point, to the left and to the right, it changes sign from either positive to negative or negative to positive. So if I drop my calculator and I put in my function that I have here, x cubed minus 2x squared, and then I'm going to put the derivative function and the second derivative function in here. So n deriv vars y vars function y1 comma x comma x. Oops. Let's go back. Comma x comma x. And for y3, we're putting the derivative of the derivative. So now instead of putting y1, we're going to put vars y vars function y2, because we want to take the derivative of what's in y2. So we want to take the derivative of the derivative. And for these, I only really want to look at the second derivative. So I'm going to turn off y1 and y2 and graph it. And it takes a little bit of time because the calculator needs to be doing all this differentiation, and it's not the easiest thing for it to do. So here we have, this is our second derivative, and we need to know, and clearly it goes from a negative value to a positive value, a negative value to a positive value. So it is switching signs, and we need to find out what is that value there. So we can press second calc. We want to find out that 0, because that's a 0 for the function. It's when my function equals 0. So I go to the left of the point of interest. I'm at the left of it. I press enter. I go to the right of it. I press enter. Guess, just press enter. And it's going to give me the value when my second derivative equals 0. So what we just found out is that we're going to have a point of inflection when x equals, well, we know what that decimal approximation is. When x equals 2/3, there's going to be a point of inflection. And we also know that, this is a graph of my second derivative, so y double prime. It's going from a negative value to 0 to a positive value, so it's going in this case. So we know that it's going from concave down to concave up. And that's what we just found. And just to kind of confirm that, let's look at a graph of the function itself, just to say, at x equals 2/3, does it go concave down to concave up? So we turn off y2 and y3, we press graph, and we notice here at 2/3, like we would expect, we've got a point of inflection where it goes concave down and then concave up.